So what I'm going to talk about today are amplifiers. So the circuit I handed out is a transistor amplifier, but just in general, let's go through a couple of things about amplifiers, and then we'll move on to that particular circuit and analyze it. We've already seen it as just as a voltage divider base, voltage divider biasing circuit, but now what we'll do is we'll use it to do something, which is amplify. So let's talk about amplifiers first. Amplifiers, so a symbol for an amplifier is this triangle right here. So this is a symbol for an amplifier. An amplifier has an input, so we'll put this here, this is input. It has an output. And the other thing it has some kind of power source. So we'll put right up here, we'll introduce a power source. And that power source will usually be a DC power supply. So we'll have to add some energy in there via a DC power supply. Okay? So when you have an amplifier, you'll usually have an input signal. So we'll have a small input signal. And coming out of it, we're going to have a facsimile of it, hopefully the same signal, but with more energy added to it, more power. Now, an amplifier can amplify three things. It can amplify voltage, it can amplify current, or both of this, and it can amplify power. So we can have voltage amplifiers, we can have current amplifiers, we can have power amplifiers. So when we have a voltage amplifier, we'll talk about a voltage gain, which we call AV, and AV will be V out over V in. When we have a current gain, we call that AI, and that'll be A out over A in. And when we have a power gain, well, that'll be AP. The AP is actually a factor of the voltage gain times the current gain, and that will be power out over power in. Okay? Now, the circuit we're going to be looking at is predominantly a voltage amplifier, so we should have voltage gain. So that means if we put a small voltage in, we should get out of it larger voltage. Now, when you build an amplifier, you usually build it in multiple stages. So what you've got on your sheet there, what we're going to do in the lab, well, that is just one stage of an amplifier. An amplifier system as such will have stages for voltage gain, it might have stages for current gain, and then maybe stages for power gain. When they're put together successfully, no, that's not the word I want to use.
Sequentially?
What's that?
Sequentially?
Well, sequentially, that works. There you go. So they're put one after the other. Thank you. And they combine their efforts to give you amplification from beginning to start, from beginning to end. So, for instance, let's say, okay, something you guys might know, like a stereo power amplifier, like you have for listening to music. Well, it'll take a very small signal, it'll amplify it. When it gets to the end, it's very important if it's driving with speakers, for instance, well, you're going to need a current amplifier of some sort there to be able to provide the current to a low impedance load. So there's voltage, there's current, together they form a power amplifier. In your business, you're going to use amplification, probably in instrumentation, where you're going to have a sensor at one end of the plant that's producing a small signal, and you're going to have to send it to some other end of the plant, and somewhere between you're going to need amplifiers to boost the signal up to be able to send it down lines that have a lot of resistance in them. Okay, digital signals the same thing too. They use amplifiers to move that stuff around. If you take a look on a telephone pole, you look at the cable company, those big green boxes they got, those are amplifiers. So they're going to move a signal from here all the way to Cape Rail. They're going to be amplifiers along the way to kind of rebuild, boost the signal back up to get it. So amplifiers are kind of an important thing to know about for you guys. All right, so that's just the basics right there. So we're going to move on to the circuit here. So I'm just going to redraw a couple of things. And the first thing we're going to just revisit that we've done before is we're going to revisit the DC analysis of it. So this is a 2.2K. And I don't know, the beta for a transistor, typical transistor, this is a 39, a 2N, 3904, typical beta 175. Not that it matters, we don't need it for that, but anyway, we'll talk about it anyway. So DC analysis. Excessive. Sorry, I think it's excessive. That's the word I was looking for. I didn't have my coffee this morning, so it's not good with words. All right. So this is voltage divider bias. So the first thing we're going to do with DC analysis, you'll notice that the piece of circuit I have here doesn't have the capacitors that, let me turn that over here. It doesn't have the capacitors like you have on your page yet, because the capacitors are going to be part of the AC part of the circuit, and we're just going to do the DC part, just for now, and then we'll move on to analyze how this thing actually amplifies. So first of all, we've got a voltage divider. So what I'm going to want to know is the voltage right here at the base. That's the first thing I need to know. So to do that, I'm going to say, well, the voltage at the base, what I'm really looking for, if you take a look at this thing, this is, let's say, R1, this is R2. So what I'm really looking for base to ground is actually the voltage on this resistor right here. That's what I'm looking for, VR2. So if I want the voltage at the base, I want really VR2. And since we have a voltage divider, well, our voltage divider loss is, well, you put R2 over the sum of R1 plus R2 to be able to find that, times the 12 volts. So this is going to be 47K over 47K plus 68K times 12. So you should come up with a voltage there. So it's going to give us a voltage. So take your calculator, figure that out for me. Yeah, I'm feeling 4.9. 4.9 volts. That's what you should get at the base. Okay, so right here, 4.9 volts right at the base. Okay? So if I go from the base to the emitter, well, I lose 0.7 volts. So at the emitter, I'm going to have 4.2 volts. All right, lose 0.7. So that means that the voltage that's on this 2.2K, which we call resistor RE, this one appears resistor RC. So on this resistor, the voltage on this resistor is 4.2 volts. Okay. So with that, we can find the emitter current, so IE, which is equal to IC plus IB, because IB is so small, while IE is almost equal to IC. So we can say that IE, which is almost equal to IC, is equal to the 4.2 volts divided by 2.2K. And that's going to give us our current coming down this way. It does. So 4.2 divided by 2.2K. Do that. Put that through your calculators. And I believe you're going to get something like 1.9 milliamps.
1.9.
Okay. So 1.9 milliamps. So the current running through here is 1.9 milliamps. All right? Now, because we've got 2.2K down here, it's got 4.2 volts, and we've got a 2.2K up there, and it's running the same current as the one down there, we can, again, assume that right up here, we'd lose 4.2 volts on resistor RC as well. Makes a lot of sense, right? You've got the same current running through the 2.2K here and the 2.2K there. They're going to have the same voltage drop. So if I wanted the voltage from collector to emitter, VCE, I would simply take whatever I started with, 12 volts, subtract the voltage on RC, subtract the voltage on RE. So this is 12 volts minus 4.2 minus 4.2, and that's going to give me my voltage across VCE. So we'll take 12 and take away 8.4. What do you got? Okay, because you have 12 volts, you've lost 4.2, you've lost another 4.2, so that gives you the voltage across collector to emitter.
It's 3.6.
3.6. So 3.6 volts is what we have. From collector to emitter. So now what I'm going to do is I'm going to draw a load line. So we're going to make a little graph over there. We're going to put VCE in this one. We're going to put IC over here. And we're going to put two dots here. So we're going to put IC saturation at this end. And we're going to put VCE cutoff at the other end. This value would be 12 volts. Roughly. So, here's how this thing works. My little graph here, which is IC versus VCE. If the transistor in this circuit was being operated as a switch, as we first saw, the transistor would either be here, fully on, so this is like this point means fully on, as much current you could run through it, or it would be fully off. with no current going through and all the voltage falling from collector to emitter. So if it was a switch, it would be either here or here. But it's not. In this case, we've biased it. And that means what we've done is we've put it on this line here. So we have a line. Let's see if I can draw a straight line this morning. That's pretty good. And what's happened here is we've put our transistor somewhere between being fully off and fully on. So it's sitting right now, 3.6 volts, so that's about right here. It's sitting here. This is called the Q point. So when we're using it as an amplifier, it is going to be hopefully sitting somewhere on the line. The closer to the middle, usually better. This one isn't perfectly in the middle, but the Q point here is, well, let's see here. We've got an IC, ICQ, and we've got a VCEQ. And those are, according to what we've calculated, 1.9 milliamps and 3.6 volts. So if we can draw this thing down, this is about 3.6 volts, and this is 1.9 milliamps. It could be centered better, but this is where we are on the line. And as an amplifier, when we start using it as an amplifier, we're going to make this point go up and down. That's what we're going to do. All right? So we're going to apply a sine wave somewhere, or whatever wave we want. We'll make this point move up and down, but it's going to be between these 2 points. It won't be fully on or fully off. It's somewhere in the middle, conducting. That's why they call it a semiconductor. Okay? So if we wanted to adjust our Q point and put it more into the center, all we have to do is play around with the biasing resistors, and we could actually tweak these, make one a little higher, a little lower, and we could move the Q point closer to the center, which would be ideal. And you're going to see why tomorrow when we build the circuit. Okay? So I'm going to let everybody catch up to me, put all those notes in, and then what we'll do is we'll move to the AC part of the circuit. So what I'm going to do is, does everybody have all of this written down for us? Okay, so I'm going to add some components, and I'm going to talk about this particular thing in terms of its AC analysis now. So I'm going to add this capacitor here, C1. So the input signal, Vin, the little signal that's going to go in, is going to go in at Vin through C1. And the signal is going to come out at the collector right here. This is C2. This is going to be called V out. And C1 and C2 are going to be referred to as coupling capacitors. So the signal, little signal we're going to put in, I'll just put a sine wave, it could be anything, but the little sine wave that I put in here is going to go at C through C1, and the signal is going to come out. By the way, the signal is going to come out is going to be flipped over. It's going to be 180 degrees out of phase. So it's going to be coming out and hopefully bigger. Okay? It's going to look just the same, but bigger. And it's going to come out at the collector. Now, because the signal goes in at the base, comes out at the collector, and that the emitter is not used, we refer to this type of circuit as a common emitter amplifier. okay? Because we're not using the emitter for input or output. Now this type of amplifier is more or less a voltage amplifier. There's also such a thing as a common base amplifier, which is a power amplifier, and there's also a common collector amplifier, which is a current amplifier. Okay, so there's variations of how you can, take the input and the output where you can place these things. But this particular configuration, the common emitter amplifier, is a voltage amplifier. If you go on Moodle, I've posted an article, something off the web, and you can go read that. And it's on this particular amplifier. There's also literature in your book. So you go in your book, you go read up on common emitter amplifiers, it's in there. All right? Now, in your circuit, there's a third capacitor that's added. So I'm going to put this other capacitor right here. So right over here, there's another capacitor right here. It's called C3. And C3 is a bypass capacitor. Okay. Now, signal does not leave or come in from that thing. It is actually there for a reason, and I'll explain that in a second. Okay, so C1, C2 coupling capacitors, C3 a bypass capacitor. Now, the thing with the capacitors, the reason they're important there, is the capacitors only let AC signal go through. Capacitors block DC. So whenever DC biasing is going on inside the amplifier, it's not capable of leaking out to the next stages, all right? It stays inside of here because the capacitors block the DC from going through. The capacitors let AC go through, but they don't let DC go through. Oh, there's another thing I've added in my circuit. There's also, I've put a load resistor here. Just gonna add that. Our load. And this load resistor is the value of 10K ohms, okay? Now, before we go on, there's a little quantity in there, just because we're shifting over to AC analysis. There is something I'm going to introduce in there, and there's this little thing called R prime E, which is the emitter resistance. We haven't spoken about, but anyway, R prime E, this thing, R prime E, at 25 degrees Celsius, is going to be equal to 25 millivolts divided by IE. So if we take 25 millivolts, this is a given here, okay? This is a little formula you can put in your notes, your cheat sheet. So 25 millivolts, and we determined that IE, which is the same as IC, so this is IE, is equal to 1.9 milliamps. So if we take 25 millivolts and we divide it by 1.9 milliamps, we're going to get something like 13 ohms. Somewhere around there. Give that a shot.
Yeah, 13.16.
13, yeah, okay, we'll just put 13 ohms. So 13 ohms. So this little resistance right here, this R prime E, counts for about 13 ohms. We're going to need that for our gain calculations. Because the next thing we're going to do is we're going to figure out, well, how much voltage gain would this thing give us? Okay? So let's go through a set of formulas to help us figure out the voltage gain of this particular amplifier. So I'm just going to record that over here that we figured out R prime E. It's 13 ohms. So a few more formulas that you're going to save. So this one's important. All right. So once AV, so I'll give you a formula for AV. First one is your voltage gain. So this is going to be with the bypass capacitor C3 and the load resistor RL. The load resistor, by the way, kind of represents the next amplifier that's coming up. It's the input impedance of the next amplifier. So if they put the load resistor there for, it's kind of representation of, like, next thing you hook up another amplifier to that, and that's what our load represents, the input impedance of the next amplifier. Or it could be the speaker you're driving or whatever, okay? It's doing work on something. So if you have C3 and R load, the formula for voltage gain is going to be the following. It's going to be RC in parallel with RL over R prime E. That's going to be the voltage gain. And we'll calculate it. We'll see what it's going to give us. And tomorrow we're going to build a circuit. And we're going to check to see that it's actually what, pretty close to what we calculated. So RC in parallel with RL is going to be 2.2K in parallel with 10K over 13 ohms. So go figure out what that's going to be. It's going to be something 100 and something. I don't know what, but. So 2.2 in parallel with 10K is about 1.8K over 13 ohms. Take your calculator, give me a number.
138.5.
138. Okay, let's see what that means. It has no units, eh? It's a gain. So it's a ratio. And it actually represents, this 138 actually represents V out over V in. That's what we said voltage gain was. It's 138. That's what we're calculating. So here's what it means. It means that if I put 1 millivolt of signal here, which should come out at the other side, okay, is 138 millivolts. That's what that formula says. If I put 1 volt, well, it would say 138 volts. The only problem is I've only got 12 volts to work for, so we can't put in 1 volt. We're going to get distortion. We can't get more than 12. And when I'm going to have you build a circuit, I'll probably tell you to put in 10 millivolts, and we're probably going to get about 1.38 volts out as a signal size. But we can't exceed 12. It just can't do it. All right. But that's what this thing does. It'll take a small 1 millivolt signal and it'll bring it up to 138. In fact, as I said, whatever comes in here also gets flipped over 180 degrees. So in justice, we should say that the gain is minus 138 on this particular type of amplifier. What comes in at the base, compared to the collector, when you go up, the signal actually goes down over here. So there's a 180 degree inversion from base to collector. All right, so that's the equation. So this equation up here is the equation you would use if you have C3 and R load. So I'll change it a little bit. Here's the next thing I'm going to do. What if we have, okay, no C3, but we have our load? Well, the formula will change to this. AV will be equal to RC in parallel with RL, but it'll be R prime E plus RE. That's what happens to the equation if we don't put the bypass capacitor there. So this would become something like 1.8K over, well, let's see, this is 13 ohms plus 2.2K. So this is roughly 1.8K over 2.2K. That's going to give us
.8.
Ooh, that sucks. That's not a gain. That's an attenuation. What it's that number tells me that if I put in 1 millivolt, I'm going to get 800 microvolts at the output. I'm not getting a gain. So C3 is actually really important to get gain in this amplifier. If I don't have C3, I don't get any gain. The amplifier won't amplify, it'll actually attenuate. That sucks. Okay, so let's do another variation. What if I have C3 and no load? RL. No R load. Well, the formula becomes this. It says AV is equal to RC over R prime E. So the bypass capacitor is there. RE falls off. We don't have RL. It falls off. So this becomes 2.2K over 13 ohms. So the gain should go up. So 2.2K divided by 13 ohms. What do we get? 159. 69?
Yeah.
So the gain actually goes up. So if you don't have to put any energy into another amplifier or a load, you'll actually get more signal at the output if you don't have a load resistor. The load resistor actually drops the gain down. Okay? So things to remember, C3 jacks up the gain, and no RL also jacks up the gain. If this resistor was bigger, let's say 100K, well, the gain would be higher. The more current you have to pull out here, the less gain you have. So the higher this R load is, the better, and it's also a good idea to have C3 if you want some gain. It'll jack up your gain. Now, some amplifiers don't need C3. Sometimes this resistor down here is low and doesn't take much away from the gain. Okay? And sometimes putting C3 will give you too much gain. So sometimes you can have an amplifier without it if this resistor is low. But in this case, because we had a 2.2K, putting C3 actually gave us something we could work with. All right? So what we'll do tomorrow is when we build a circuit, the first thing we'll do is just build the DC part without the capacitors. So without the capacitors, without the load, we'll verify the DC to see that it comes close to what we calculated. And then we'll put the components on there. We'll apply a signal to the circuit, and we'll put a probe at V in, and we'll put a probe at V out, and we'll compare one to the other, and we'll actually see if there's a gain. So what we do when we measure voltage gain, we measure the voltage going in, we measure the voltage going out, and then we do a ratio, and it tells us what the gain of the amplifier is going to be. And hopefully when we do it with all the parts in, we'll get something around 138. We probably will. Okay?